All right, good morning, guys. So today you are doing topic 2, SAS 3, pages 35 through 41, and this is the exponential function and its inverse. So yesterday in class we talked about the linear function and its inverse. So if you were not in class yesterday, or we as a class did not finish up, I want you to go back and watch the video that I posted about that and finish that up for me. All right, so we are going to go ahead and start. And this right here, this is called the Sierpinski triangle. A Sierpinski triangle is a special geometric shape that is very complex, detailed, and infinite. Remember, the word infinite means it just keeps going and going and going. In that, it can never be finished. To create the Sierpinski triangle, first you start with a triangle, okay? Then you connect the midpoints of each side of this triangle to form 4 new triangles. Ignore the inner triangle, which points down, and repeat the process to divide the outer 3 triangles again. If you look to the right, the animation shows it. So I'm going to play it again. So first, we start with a simple triangle. We connect the midpoints to form 4 new triangles. So now we have 3 blue and 1 white. Same thing again. The midpoints, connect them. The midpoints, connect them. Okay? Midpoints, connect them. Okay? So here is just 4 iterations. But, however, we know it says it's infinite, so it just keeps going and going and going. Now, keep in mind, right here, it says, repeat this process to divide the outer 3 triangles again. Remember that. Outer 3 triangles again. So, now on the next page it says, the Sierpinski triangle is an example of a fractal. All right, so on number 1, I want you to write down the definition of a fractal. The definition of a fractal is defined as a geometric shape that can be subdivided in parts, each of which is at least approximately a reduced size copy of a whole. So you'll see everything in that Sierpinski triangle is a triangle. However, each iteration becomes a reduced size copy of that whole big blue triangle in the back. Okay? All right, so now, number 2 says, the table shows the number of upward triangles in the Sierpinski triangle. Notice that instead of a pattern of constant addition, the data exhibits a pattern of constant multiplication. The number of upward triangles produced in each new iteration is 3 times the number of upward triangles in the previous iteration. You can model such data with an exponential function. Can you complete the table to find the function rule that models the relationship between the number of upward triangles and the number of iterations? When you are finished, check your work. All right, so on number 2, it asks us, what pattern do you notice in the number of upward triangles? Well, what does it tell us? The data exhibits a pattern of constant multiplication. That is because from 1 to 3, I'm multiplying by 3. From 3 to 9, I multiply by 3. 9 to 27, I multiply by 3. Okay, so on number 2, I want you to write constant multiplication equals 3 times the number of upward triangle in the previous iteration. All right. Number 4, it says, what type of function could model the data in the table above? Well, think back to SAS 1 in topic 1. We talked about exponential functions having that constant multiplication. So for number 3, we've underlined it. What type of function could model the data in the table above? Exponential function, because it has a constant multiplication. Okay? Now, flip over to number 4 on the back, and we want to figure out the rest of this triangle. So, before you hit check, I want you to try to work this on your own. So, keep in mind that we went from 1 times 3 is 3, 3 times 3 is 9, 9 times 3 is 27. So, next we should do 27 times 3 equals whatever, and whatever times 3 equals whatever. So now your turn to fill in the whatevers. So you should have gotten 81, and 81 times 3 is 243. So that would go in our written description and our upward triangles. Now, look at the process. 3 to the 0 power, 3 to the 1 power, 3 squared, 3 cubed. In order to get 81, I would need to say 3 to the 4th. In order to get 243, I would need to say 3 to the 5th. Do you see a pattern? Okay. What is the process? 3 to the n, the number of iterations. Okay. So fill out that chart. If you go to number 5, I want you to predict what your function rule would look like. Okay, so look at your values. Everything is increasing, and it's increasing by more and more each time. So knowing that it is an exponential function, we know an exponential function looks similar to a Nike sign. So I'm going to bet it looks something like this and maybe has a curve like that. So if I hit check, it will show me a similar graph that I have drawn and that you have drawn. All right, we're going to skip number 6 and go to number 7. Okay, So it says, now that you have represented the relationship between the number of iterations in the Sierpinski triangle and the number of upward triangles numerically, graphically, and symbolically with a function rule, you can use any of these representations to find the number of upward triangles in any iteration. For example, how many upward triangles are in the 10th iteration of the Sierpinski triangle? All right, your function rule was y equals 3 to the n. N was our number of iterations. So we're going to plug in 10 for n. So we have y equals 3 to the 10th. So that would be 3 times 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 3 and times 3. 10 times. All right, so 3 to the 10th. Oops, did not mean to click off that. 3 to the 10th is 59,049 triangles. So that would mean if you do this iteration 10 times, that is how many upward triangles you would have in the 10th iteration. Okay? Now, on number 8, it says, now reverse the process. Suppose you want to know which iteration has 531,441 upward triangles. See if you can find the answer, then compare your answer to the one given here. All right, so we would write this function as 531,441 equals 3 to the n. Now, do we know how to solve that at this time in Algebra 2? Algebraically, no, we don't. I cannot just divide that by 3 because that n is in the exponent, okay? So, what I want you to do if you have your own calculator, you can do it this way. Go up to your y equals, type in 3 to the x. Remember that variable can be anything. Okay? That's our function rule. Hit second graph, and it brings up the table. Now, we are looking for when y equals 531,441. All right, so right here, here's our y, but what is our x? 12. So, in this case, 531,441 triangles equals 3 to the 12th power. So, n equals 12. Okay? Now, if you don't have your own calculator, up here on Agile Mind, I want you to go to graphing. All right. And you were typing in 3 and use the a squared. Oh, not a squared. Let's do this. The a to the b and type in x, like so, and it brings up that same graph. All right, now if you zoom way, way, way out, we are looking for when y is $531,000. You must keep going, keep going, keep going. All right, you have to kind of play around with this graph and get it just right. But we are pretty close. Here is 500. Here is 541,000. And they meet right here. And this is on the 12th spot. All right, so you can also do it that way until we learn algebraically how to do this. Okay? All right, so if you click here, it'll tell you the 12th iteration. Now, next page, number 9, says, let's see. Complete the table to show the inverse of y equals 3 to the x. Then complete the scatter plot. All right, so remember, our original table shows us on our paper zero, 1, 2, and 3 was 1, 3, 9, 27. All right, now if you look, all right, now if you look at the one on the screen, the Agile Mind one, they have already swapped it for us. So this is the inverse. Our new x is here, and our new y is here. So take a minute and fill out that chart on number 9. All you're doing, remember, is swapping the columns. You are swapping the values, okay? All right, and if you click to the next page, it will show you the same thing. It swaps, and it swaps, and it swaps, and it swaps. Now, notice the blue is the original. Those points are already plotted on your scatter plot. And the red is the inverse. So you need to fill out the red by just swapping the values. Now, go ahead and plot those red points also on the graph. So we have 0, 1, 3, 1, 9, 2, and 27, 3. And you'll notice that it is the opposite of the blue dots. Now, This right here leads to number 10. Notice that we already know that y equals 3 to the x is that exponential function. All right? Now, the red. What type of function models this inverse? All right, this is called a logarithmic function. Number 10, a logarithmic function. All right, so what I want you to write for each exponential function, y equals b to the x, that's the exponential, comma, there is an inverse log function, y equals log base b of x. And we will talk so much more about this in a later topic. But for now, you need to know the inverse of an exponential is a log. All right, we are going to skip number 11 and 12. So let's go ahead and go to 13. It asks, very, very simple question. How do you denote the inverse of f of x? All right, I'm going to circle it, or I'm going to highlight it. And I want you to write inverse equals f of -1 of x. Anytime you see this that I have starred, you must know it literally means inverse. That is just a sign that tells you inverse. Okay? All right. Now, let's look at 14 and 15. All right, so 14. What is the inverse of y equals 2 to the x? All right, this is exponential. The inverse, please write this down, is a log. All right? Now, notice the y does not change. Okay? Now, look at the exponential. What does b equal? B equals 2. And what does x equal? X just equals x in this case. All right, so you were using these two values and you're putting them in this log. So y equals log b of 2 and our x. That's as hard as it gets. Okay? All right, now don't worry about graphing them. We will graph them in class on Friday. Okay? In class on Friday. However, if you were not in class, they look something like that. But we will go over that in class. All right. Now, let's look at number 15. F of x equals 10 to the x. Remember, f of x means y, guys. This is exponential. We are going to log all right. Y equals log. What is my base? What is my b? 10 of x. Now, if this is the original, the inverse, what did we just write on number 13? What denotes the inverse? F of negative 1x. These are the same, just like those are the same. Okay? Now, I want you to do B and C on your own. They are just like 15A. If you want to go ahead and graph them, you can. But remember, we're going to graph them in class on Friday. Have a great day. See you all then.